Welcome, everyone. So this is a rather short presentation, so we're going to dive right into business. This is a talk on profiling Node applications, and so I hope you have familiarity with Node, or maybe you have a deployment that has Node inside, or maybe you're just considering, like, what are the tools going to look like for performance monitoring, for performance investigations once you introduce Node.js into your lives. So that's kind of what this talk is about, investigating production issues, performance issues in Node applications on Linux. There's also other platforms, of course, that you can run Node on, but we're not going to look into those. We only have the 30 minutes here. And what I want to talk about is some production-ready tracing tools that you can use with Node applications, monitor CPU utilization, investigate various operating system level events that your Node.js process might be causing, and that sort of thing. And we'll also use flame graphs to visualize some of that information as a little bonus along the way. So in terms of tools and operating systems, for those of you that might have like deployments on other OSs other than Linux running Node.js, there's alternatives for some of the tools I'll be using for other platforms as well. But again, we'll only look into the Linux options in this presentation. So again, I'm just going to dive right in, and I have a number of scenarios that we'll go through. They're structured like demonstrations, but there's just going to be all on the slides. So the first thing we're going to be doing is looking at the built-in V8 profiler. And V8, as you know, is the runtime that sort of Node sits on top of. So V8, turns out, actually has a built-in profiler that we can use to profile Node applications. There's a couple of problems there, unfortunately, even though it is built in, which is pretty nice. The problems are that the profiler generates a log file, and you don't really have a lot of control over that. The log file can grow pretty fast. So if you plan on doing this in production, you'll probably get gigabytes of logs over an hour or so of profiling, so it's not really practical there for long-term use of that sort. This profiler also has the little-known problem of only profiling your main thread, which for a lot of Node applications is exactly what you want to do, just profile the main thread. But if you do have worker threads doing CPU work, as you might, it's just not going to see them at all. So it's going to report that you're not using the CPU, even though you have worker threads running in the background. With that said, it's built in, so it's worth kind of looking at first. So here's the scenario that we have. We have this Node process running in the background and consuming lots and lots of CPU. So I've just ran top to see that. And then we launch our Node process with the profiler inside. And that's the --prof switch. Now, there is also a way to turn on the profiler once you already have the process running, but you have to sort of build your application for that, so you have to call a couple of APIs. If you haven't done any preparation work at all, you have to restart your Node application to do profiling, which is, again, kind of a major boo-boo, and you might not want to do that in production. Once you've done that, you get these enormous log files that the profiler generates. And then there's also a built-in switch to the Node binary, which analyzes that log file and produces a report. And that report looks kind of like this. It gives you a summary of what kind of things in general are taking time in your Node application. So is it JavaScript code you've written? Is it C++ inside the runtime or C++ modules? Or is it the garbage collector even? And we'll come back to GC issues a little later. So once you have a general picture of what kind of language, at least, or runtime component in your process is taking up time, you also get a nice summary of which functions, or which individual functions in your application, JavaScript or C++, are using up lots of CPU. So that's kind of what the profiler is supposed to do. Again, unfortunately, it has a bunch of disadvantages, which is why I can't really recommend it for production use. In development, it's pretty handy, it's pretty simple, and the report is usually fairly easy to read. So this one, for example, tells us that I am calling this function called pbkdf2, and that's responsible for 90-something% of my CPU utilization, which is a lot. And what you see on the very bottom there is the actual call stack. So this whole section here is the actual call stack leading up to that call from my code. So the very last thing you see highlighted is just my JavaScript code, users.js, line, whatever. So that's an example of using the Node built-in profiler. And again, it has its problems, so I'm just going to switch to the next thing. And the next thing for old-time Linux users should probably be perf, which a lot of you definitely have seen. It's a multi-tool built into Linux for performance investigations. If you haven't used it with Node.js before, that's perfectly acceptable because it's not like very trivial to do, but it's definitely possible. Perf itself has a bunch of capabilities that have nothing to do with Node.js, and the only link between perf and Node is going to be something very small that I'm going to mention in a moment. So once you have perf installed on your Linux system, you can do CPU profiling with perf as well. Again, our objective is to diagnose high CPU usage. We're just going to do it in a slightly different way. And what we get from using perf is that we can attach to a running process. So we don't have to launch our node process with some extra profiling switches. You can just attach to a live system. You can profile native code, and you can profile the kernel code as well. So you get a more comprehensive picture of what your system is doing, not just the node parts, but everything else as well. The problems are it's Linux only, so it's not cross-platform like the V8 built-in profiler. And perf also has a problem where it writes lots of data to a file. But at least you have more granular control over the amount of data gets written and the frequency that perf uses for its CPU profiling. So here's what it's going to look like with perf. You run this magic incantation, which I'm going to break into pieces here. So first of all, it's going to require root. You can use perf as standard user in some scenarios under some conditions, which I'm not going to go into. But if you want to profile the whole system, you probably need root for that. Then you specify the process filter. So we only care about the node process. We don't need, in this example, to profile anything else. We specify the profiling frequency. So this is how often perf is going to sample the CPU to see what the process is doing, what the node process is doing right now. And that's a frequency in hertz. So that's 97 times per second. It's going to sample our process. And finally, that G switch is for stack traces, which means I want to capture a stack of what the process was doing and not just the current function, which is needed to get a comprehensive profiling report. So once I've done that, I can run a command called perf report to get a report of what my node process was doing. And this is what I would get, which is not really useful. It's also going to span multiple handfuls of screens, and it's only going to have addresses inside. And the problem here is that perf is not designed to parse Node.js functions, JavaScript functions, addresses, that sort of thing. Perf needs access to symbolic information, to debug information, in order to translate these addresses to function names inside your JavaScript application. So that's something common across additional languages as well. It's not just the Node.js problem. You'll have the same thing with Java. You'll have the same thing with, say, Python. You'll have the same thing with any language that uses some kind of interpretation or just-in-time compilation, and Node just happens to do that. So here's what you do to accommodate. You have to run Node with a magic switch again. But this time, the magic switch only tells the Node runtime that whenever it compiles a function, it has to also write some additional information to a text file, to a map file, which maps that function's name to the generated code, to the generated address. So that's kind of Node adjusting to the way perf works. Perf has a way of looking for these files by default. So Node just at some point added a switch which generates those files at runtime. Now, this is not the same thing as running the profiler ahead of time, like we did with the V8 profiler, because this doesn't turn profiling on. It just sort of enables this extra information that you would need to do profiling later. And so that's something you can probably afford doing in production, although there are some issues there as well. The map file, which maps functions to addresses, can grow pretty big as well. And Node has a compiler which discards code and recompiles it occasionally. So essentially, the file can grow in an unbounded manner because your code can get recompiled again and again. And so you still do have to kind of take care and trim that file once in a while. But that's something a lot less expensive. And once you've done the whole thing and you run perf report again, perf is going to report actual function names in your JavaScript application. It's going to be able to resolve the whole stack and show you useful data. Again, in this case, what I've highlighted is users.js line 46. And the rest of what you see is just a truncated call tree leading up to the expensive functions. It's not really a very useful way of visualizing CPU profiles, especially if they're very large and complex. So we'll definitely switch to a slightly different visualization tool in a moment. But that's just the basics you have to sort of go through to get even a text report dumped out to the terminal. Now, the report for a quite simple app that I've done as part of my preparation was 18,000 lines. So this little snippet is part of a larger report, which is 18,000 lines. And that's a really very, very small Node application that's just basically not doing a lot other than hashing strings. So it's not really handy to go through scrolling these handfuls of text, these 18,000 lines. And this is where alternative visualization methods come in. And one that I think all of us should be familiar with is flame graphs. So some of you have seen flame graphs before. I see some nods in the audience. Flame graphs are a visualization method that Brendan Gregg came up with for stack traces. So if you have lots and lots of stack traces, for example, for CPU profiles like we did before, you can generate a single diagram out of the whole thing. The diagram is going to be interactive, so you can zoom in and out, you can filter stuff, you can search, and visualize the whole tree of function calls that you have in your application. Now, again, we don't have a lot of time to spend on flame graphs, but I definitely recommend that you check them out if you haven't used them at all, or if you haven't used them with Node.js, it's definitely something you should be looking into. To generate a flame graph, Brendan has up on his website, up on GitHub, sorry, he has a bunch of Perl scripts. And it's kind of weird, you know, you have a Node application and you use Perl to generate flame graphs. There's also some Node.js alternatives. So there's a couple of projects up on GitHub that are pure Node.js applications which generate flame graphs as well. The output is kind of the same, it's just the tool that's different. So here's what a flame graph might look like for one of my examples. Every rectangle you see is a function that we encountered in our profiling. The colors here are just random. They just help sort of differentiate the different functions. Whenever you see a function on top of another function, so essentially the vertical axis, it's the call stack. So if you have a function on top of another function, it was called by that other function. And the final important piece of information is that the wider something is, the more prominent it was. In our case, the wider a function was, the more CPU time was spent there. So this is how you read this thing. You basically look for the widest towers first, and then you start navigating them to figure out what this part of my code was. Now, I don't know if you can all see this, but in this case, all of my towers essentially end in the same place. So this is PBKDF2, this is PBKDF2, it's here as well. So I have a bunch of places in my node process, but they are all bottlenecked on the same thing. And that thing is that PBKDF2 function, which is hashing strings in my example. But that's a lot easier to read than 18,000 lines of terminal output. So this is why we're doing this. So that was the built-in V8 profiler and perf. We already have a couple of useful performance tools that we can use with Node applications. But there's something fundamentally wrong with both of these. And perf specifically also suffers from this issue. And that's the issue of having to generate lots and lots of data into a file before you can process the results and before you can get a summary of your investigation. So that's just how perf typically works. You run perf, you collect a bunch of data to a file, and then you do post-processing on that. There is a way of using perf in a more real-time way, but typically this is how profiling with perf would look like. You would generate a perf.data file, and then you would process that file in user space. Now, I've done an experiment just for fun. I've downloaded a file over a 1 gigabit link, and I've recorded every single receive event on my system, every network receive event. I haven't recorded the packets. I've just recorded the receive events, just the metadata. And that was 20 megabytes of data per second. So clearly, you can't record like this for an hour and then analyze the log for looking for something or doing a summary. It's not going to scale. So that's one of the key issues with perf that's sort of paved the way for alternative approaches. And one of these, which I'll be also talking about in my workshop later today, is BPF, which is here contrasted with the perf way. So up on top, you see, again, the perf approach. You have a bunch of data written to a file, and then you analyze that file in user space. The BPF way of doing things, which is a technology that was introduced in Linux a couple of years ago, the BPF way of doing things is that the aggregations, the summaries, the flame graphs, they all get generated right at the source, right in the kernel. And the only data that you have to share with user space is a small summary which can be displayed immediately and doesn't require any expensive post-processing. And you also end up discarding all the data you don't need. The data that was already processed, you don't have to just sort of store it there just in case. You can discard anything you don't need. So again, this is just a very, very basic overview of how BPF helps. And we'll see a couple of tools based on BPF which can be used to profile Node applications and extract some useful information without a high overhead, without having to record a lot of events into a file. So to use BPF, we'll use an open source project called BCC BPF Compiler Collection, which I also encourage you to check out. It has contributors from a bunch of folks from different companies, and it's actively used today in production systems. It's got a very wide set of tools, but specifically, there are some tools specifically for Node.js, which were introduced. I've written a couple of those. And if you're interested in Node.js profiling specifically, that's the tools you might be using from this collection. But there's a bunch of stuff here for everyone else as well. Kernel events like scheduler events, database profilers, which will tell you which queries you're executing in your database. There's a bunch of stuff there. But for Node specifically, we have a few tools that can look at Node processes and output some useful information. And one such tool is the profile tool, which is a generic profiler, which will give us the same thing as what we've done with perf and the V8 profiler before. So it's not going to be a very different output. It's just the approach that's going to be completely different. The way the profile tool works is it aggregates all the information needed to generate the flame graph or to generate a summary report. It aggregates all that information right at the source in the kernel. So you don't have to record megabytes of data per second just to get a visualization of what your CPU was doing in your Node application. That's a very important difference. The sort of only downside I see today is that BPF is only available in fairly recent Linux kernels. So you pretty much need Linux 4.1 for anything at all in that toolkit. So you might not be able to use it straight away. But again, we can talk about that later. So here's what it looks like when using the profile tool. Again, you run a magic incantation that attaches to a process and profiles it at a certain frequency. And you get a summary that can be used straight away for generating a flame graph. And you might not notice, but it's actually the same data. It's just that my flame graphs previously were zoomed in on a particular section. But the output is still a flame graph if you want them, if you want one. It's just that the profile tool doesn't record a lot of stuff to disk in order to get the final profile. And you could potentially use this approach to do continuous profiling like that, maybe at a slower frequency, at a lower frequency. So maybe you'd just sample the system 10 times per second, but you'd have the ability at a click to get a profile of the last 5 minutes, of the last 5 seconds, of the last however much time you want, without having to store every single sample just by aggregating at different intervals. So this opens the door for a lot more interesting performance scenarios. So that was a lot of CPU profiling, but there's other stuff interesting for people building Node systems, for people building Node applications that you might want to look into. And one important thing is off-CPU profiling, actually. So you know that Node has this main event thread, and blocking that thread is a major, major no-no. If you block the event thread doing something unnecessary, like I/O, database accesses, just sleeping, waiting for something, if you block the event thread, you're not processing any additional requests. That's a fundamental axiom of how Node works. And so if you are blocking your event thread, if you notice that you are getting some slow requests, even though you're not using a lot of CPU, the investigation process changes. You no longer look for the CPU hotspots. You look for the off-CPU hotspots. Like, what are the locations in my Node application where I block frequently? So am I doing lots of synchronous I/O, which is really bad? Am I waiting for something? Maybe I'm getting descheduled by the kernel because other processes want to run and they have a higher priority or whatever. So that sort of thing, which kicks me off the CPU, is what we're after now. And we have a tool for that in BCC, which is called off-CPU time. It's designed to track off-CPU time and give you call stacks of where you're getting off the CPU, where you're getting kicked off the CPU. So here's what it would look like. This is just an example of running a benchmark. So I have a particular endpoint on my Node application. This is the endpoint. The code is up on GitHub, so if you want to experiment with this later, you can. Running the benchmark, I see only 35% CPU utilization. But my request rates are not what I would want them to be, so I'm getting responses in like my 90th percentile. Over here is 200 milliseconds, and I want to improve that. So I want to get faster responses, and I want to figure out what my process is doing if it's not doing lots of CPU work. So here's what the off-CPU time magic command line would look like. We attach off-CPU time to a particular Node process. The F switch here stands for folded, so it would output data in a format that the flame graph tools are ready to consume. You can also have it output just text format designed for you to read, but that's what we do to get something that we can easily generate a flame graph from. And here's what the flame graph would look like in this simple case. So this whole giant tower that you see on the left and center, that's where I'm doing most of my blocking. That's what's blocking my event thread most of the time. And if you look at the frames, like most of it, everything highlighted here under Linux kernel, so this whole section here is kernel functions. And the BPF tools, perf as well, they can profile the kernel. So you see a bunch of kernel functions there. And if you look into the function names, you'll be able to see it has something to do with flushing files, and maybe even the fact we're flushing the file once the file is getting closed. So it looks like a file that we've written a lot of stuff to, and then we have to close the file and flush everything to disk, and that's what we're blocking on. But the interesting part, of course, is the user space part here, where you can see which part of my Node code was actually causing that to happen. And again, I don't know if you can see the exact functions there, but it's happening in a particular route in my Node application where I'm doing file I/O synchronously. So rather than using callbacks as I should, I have synchronous I/O closing a file, and when that happens, that close is just basically waiting for the data to get flushed to disk and slowing me down. So I have a couple more scenarios like this I want to show you, but before that, once we've established that we have lots of files that we're accessing, might be interesting to figure out which files. And this is no longer a Node.js issue at all. We have a generic tool in BCC, which you all might find useful, called file slower, which you give a threshold, and it will look for any file accesses slower than that threshold. And it will print out which file is getting accessed, it will print out the size of that file access, and it will print out the latency. In the latency column, it will tell you the duration of that file access. So that's what's slowing this particular Node application down. One last source of performance information that we have time to discuss today is called USDT, and it would really be amiss if we hadn't time for this. So USDT is a technology that's been available for ages, which you can use to place static probes, static instrumentation in binaries. And there's a bunch of languages shown on the slide here, like Java and Node and Python and PHP and a bunch more, which have these static probes embedded in them. Now, I know you probably don't care about the other languages because you're here for the Node talk, but if you do, then yeah, you should definitely look into using the same technology to profile these other languages as well. But looking at Node specifically, Node has static instrumentation built in for tracing HTTP requests, for tracing garbage collections, which is pretty useful. There's not a lot of these probes, but the ones that are inside Node are pretty useful. So how do you get the different observability points, the different static traces from the Node process? We have a tool for that called TP-list, trace point list. And here's what it looks like. I can run TP-list and give it a particular process ID, and it dumps out all the static instrumentation points in that process. And for Node, that includes the set I've told you about. So garbage collections, HTTP requests and responses, and there's also some stuff for TCP streams, for network streams. So each of these can then be traced. Now, in addition to these static instrumentation points, we can also trace, and that's also occasionally useful, just trace arbitrary functions inside the runtime, inside the Node runtime, which is a C++ application. And if you're into that kind of thing, the runtime has thousands of functions which you can get from objdump or that sort of tool, and each of these functions can be traced as well. So in addition to the small set of static trace points, there's also a bunch of functions in the runtime that can also be potential trace points. So here's one small example of what you can do with all of that. One example is tracing HTTP requests in a Node application without any preparation or extra support. We have a trace tool that attaches to a process and instruments these static instrumentation points and prints a message whenever they're hit. It's like a dynamic log for your application. So it has a bunch of flags, which I'm not going to talk about, but the output is just, in this case, a list of all the HTTP requests that my application is serving. Another example of the same thing, based on the same kind of concept of instrumentation, is using the UGC tool that we have in BCC, which attaches to a Node process and prints out garbage collections, including their duration. So you can know if your Node process has excessive garbage collection and where that garbage collection is coming from. And for the extra advanced bonus points, you can also do some more sophisticated stuff, like trace actual C++ functions in the V8 runtime, and in this case, get a histogram that tells you the latency of your garbage collections. So how many garbage collections you had that took under a millisecond, how many between 2 and 3 milliseconds, 4 and 7, 8 and 15, and so on. So that gives you a GC latency for your Node application. We're pretty much out of time, so the only last final thing I want to do, where's my mouse pointer? The last thing I want to do is give you a few references to look at once we're done here. Perf and flame graphs have a bunch of useful material online that you should definitely look into. USDT in Node.js is something a lot of people don't know about, the static tracing embedded in Node.js and other languages as well, so you might want to check this out as well. And BCC, that amazingly powerful toolkit, is also something you might be interested for, not just for Node.js profiling too. So the slides are here, and the demos that you can also try yourself are up on GitHub as well. Thank you very much.